You know, I have a friend who's an artist, and sometimes he holds a view that I don't quite agree with. He'll hold up a flower and say, "Look how beautiful this is," and I will agree. But then he'll say, "I, as an artist, can see this beauty, but you, as a scientist, take it all apart and it becomes a dull thing." And I think that's a bit nutty, because when I look at that flower, or that glass of water, or the movement of the clock on the wall, I don't just see the surface, I see the machinery. And when you look at the machinery of the universe, specifically, the machinery of time, you find out that nature is behaving in a way that's completely absurd. It's absolutely ridiculous. We have this intuition, don't we? We feel that time is a river that flows in one direction. You drop a teacup, it shatters. You never see the shards jump up and reassemble. We get older. We don't get younger. The past is done. The future is unknown. And we are stuck in this razor-thin moment called the present, moving forward, always forward. But what if I told you that this picture, this arrow of time that feels so solid to you, is really just a statistical accident? What if I told you that at the fundamental level, down where electrons and photons play their game, there is no distinction between past and future? In fact, it gets crazier. To solve some of the biggest problems in physics, to make the equations work, I had to introduce an idea that sounds like science fiction but is actually science fact. I had to assume that particles can and do travel backwards in time. That's right. The electron in your fingernail right now might be the same electron that was in your coffee 10 minutes ago, just traveling back from the future to visit you again. It sounds nuts. It sounds impossible. But nature doesn't care what we think is impossible. Nature just is. Today, I want to tell you about the strange behavior of time, and how a paradox about looking backward actually helped me win a Nobel Prize. We are going to take the clock apart, and we might not be able to put it back together the same way. Now, before we get into the nitty-gritty of electrons going the wrong way, we have to talk about why this matters. Why should you care if an electron moves backward? You have bills to pay. You have dinner to cook. Why does quantum electrodynamics matter to you? Well, it matters because you're made of this stuff. You are a pile of atoms, and if the rules that govern those atoms allow time to flow in both directions, then our entire concept of reality, of what it means to exist in a specific moment, is fundamentally shaky. Most people go through life thinking the world is a stage and time is the script telling the actors where to go next. But in physics, we found out the script is written in a language that reads the same forward and backward. If you don't understand this, you're missing half the beauty of the universe. You're seeing the flower, but missing the wonder of the photosynthesis inside. So, I have a proposition for you. This isn't just a physics lecture. This is an invitation to stop looking at the world with your everyday eyes and start looking at it with Feynman eyes. We are going to try to turn your intuition inside out. If you enjoy the sensation of having your mind slightly bent. If you want to join us in this honest, difficult, and wonderful pursuit of finding things out, then stick round. Hit that subscribe button, not for me, but for your own curiosity. Let's find things out together. Let's start with something simple, or at least something that looks simple, light. When you look in a mirror, you see your face. Light goes from your face to the mirror and bounces back to your eye. Easy, right? Light travels in a straight line, hits the glass, comes back. That's what we learn in school. That's what the old Greeks thought. But let's look closer. Let's ask the question, how does the light know where to go? Asterisk, imagine you're a lifeguard on a beach. You're sitting in your high chair and you see a swimmer drowning in the water. You need to get to them as fast as possible. Now, you can run fast on sand, but you swim slow in water. If you draw a straight line from you to the swimmer, that's the shortest distance, sure. But is it the fastest time? No. Because that straight line spends too much time in the water where you're slow. Asterisk, so what do? You run a little further, down the beach, staying on sand longer to maximize your speed, and then angle into the water so you have a shorter distance to swim. There is a specific path, a bent path. That takes the absolute minimum amount of time. Asterisk, it turns out light does exactly the same thing. When light goes from air into water, it bends, it refracts, it changes direction. Why? It looks like the light calculated the path of least time. It looks like the light sniffed out all possible paths and said, aha, that one's the fastest. Oh, take that one. Asterisk, this is called the principle of least action. And for a long time, it bothered me. Bothered me a lot. 'Cause think about it. The photon is a tiny, dumb particle. It has no brain. It has no calculator. It doesn't have a map of the beach. So how does it know which path is the fastest? Does it smell the destination? Does it send out little scout particles? Hey guys, check path A, check path B. Tell me which is quicker. No. That's creating a mechanism that doesn't exist. We are trying to impose our human logic, our logic of making a choice, onto a particle. Asterisk, the answer I found, and this is the heart of the path integral formulation, is much more bizarre. The electron or photon doesn't choose the best path. It takes all the paths, I mean literally, all of them. Asterisk, imagine a particle trying to go from point A to point B. It takes the straight path. It takes the curved path. It goes to the moon and comes back. It goes to the edge of the universe and returns. It goes backward in time, does a loop-de-loop and goes forward again. Asterisk, it sounds crazy to say it takes all paths. You might ask, surely, Richard, it has to be in one place at one time. And I would say, no, that's the old way of thinking. That's the classical way. In quantum mechanics, we have to sum over the histories. We have to add up every possible way the event could happen. Each path contributes a little arrow, a little amplitude, to the final answer. Asterisk, think of it like a clock. Imagine a little stopwatch attached to the particle. As the particle moves along a path, the hand of the stopwatch turns, round and round. The speed at which it turns depends on the energy. Now, for a crazy path like going to the moon and back, the time it takes is very different from a slightly less crazy path, so the stopwatch hands end up pointing in all different directions. One points up, one points down, one points left. Asterisk, when you add a million arrows pointing in random directions, what do you get? 0. They cancel each other out. The crazy paths destroy each other. Asterisk, but for the paths right near that perfect path, the path of least time, the times are all very similar. The stopwatch hands are all pointing in roughly the same direction. They don't cancel. They add up. They reinforce each other. Asterisk, so the reason light looks like it travels in a straight line, the reason the lifeguard looks like he chose the best path, is simply because all the other paths cancel themselves out. The miracle of the straight line is just the illusion created by the interference of infinite crazy H. Stories. Now, this is where it gets really interesting. This is where we have to talk about time. Because one of those crazy paths I mentioned, it involves going backward in time. Asterisk, when I was working on Quantum Electrodynamics QED, the jewel of Physics. I ran into a problem. We were trying to calculate what happens when two electrons scatter off each other. You have an electron coming in, another electron coming in. They exchange a photon, smash, and go flying off. But the math was a mess. We kept getting infinities. We'd calculate the energy of the electron, and the answer would come out as infinity. That is not a good answer. You cannot weigh infinity pounds. We had to find a way to organize these events. So I started drawing little pictures. Today you call them Feynman diagrams. But to me they were just a way to keep track of the chaos. In these diagrams, time flows from the bottom of the page to the top. Space is side to side. So a straight line going up is a particle sitting still in space, moving through time. A slanted line is a particle moving through space and time. Now look at this. Suppose I have an electron moving along and suddenly, at a certain moment, it emits a photon and changes direction. Okay, simple. But what if I have a line that zigs and zags? What if the line turns round and points down towards the bottom of the page, if time is going up? What does a line going down mean? It means the particle is moving backward in time. If you were watching this like a movie, what would you see? You'd see the normal electron moving up. But then, out of nowhere, at some point in the future, a pair of particles appears from nothing. One is an electron and the other is, well, it looks like an electron but has the opposite charge. It's a positron, an anti-electron. So now you have three particles, the original electron, the new electron, and the new positron. Then the original electron meets the positron. They crash into each other. Poof. They annihilate. They disappear in a flash of light, and you are left with just a new electron moving forward. This is what it looks like if you slice time moment by moment. It looks like creation and annihilation. It looks like magic. But if you look at my diagram, the zigzag line, it's just one continuous path. It's just one electron. It went forward in time, turned round and went backward in time, appearing as a positron, and then turned round again to go forward. This was the revelation. The positron, antimatter, is just an electron moving backwards in time. Now you have to be careful here. I am not saying you can jump in a DeLorean and go kill your grandfather. I'm talking about the fundamental symmetry of the equation in the math of the Dirac equation. There are solutions for a negative energy. People were scared of them. They tried to hide them. Dirac tried to fill the universe with a sea of electrons to explain them, but I thought, that's too complicated. Nature is simple. If you take an electron and you reverse the flow of time t2, it looks exactly, mathematically identical to a positron moving forward in time, to the universe. Past and future are just directions, like left and right. Think about slicing a sausage. Imagine the whole of space-time is a giant sausage. The length of the sausage is time. The width is space. Now you and I, we are slicing the sausage at a 90-degree angle. Each slice is now. Each slice is a moment. We see the circle of meat and we call it the present. But imagine someone moving very fast. Someone on a spaceship. Relativity tells us their now is tilted. They are slicing the sausage at a different angle. What I think is the past, they might see as the present. What I think is the future might already be in their slice. The events, the atoms, the collisions, the history, are all there in the sausage, the block of space-time. We are just crawling through it, discovering it slice by slice. But the electron doesn't just crawl. The electron can loop back. This leads to a thought I once discussed with my advisor, John Wheeler. It's a thought so big it might make you dizzy. Asterisk, we know that all electrons are identical. Exactly identical. You cannot tell one from another. They have the same mass, the same charge, the same spin. Every electron in your brain is exactly the same as an electron in a star a billion light years away. Why is nature so repetitive? Why didn't she make some electrons a little fatter or a little bluer? Asterisk, Wheeler called me up one day and said, "Feynman, I know why all electrons have the same charge and the same mass." I asked, "Why?" "Because they are all the same electron." Asterisk, imagine the zigzag I told you about. Forward, backward, forward, backward. Now, imagine that this single electron zigzags back and forth through time, enough to cover the entire universe. When it goes forward, it's an electron. When it goes backward, it's a positron. Asterisk, if you take a slice of now through this massive tangle of one single thread, you would see billions of points where the thread crosses the slice going up electron and billions of points where it crosses going down positron. We would look at TH and say, "Oh, look at all these trillions of particles." But really, it's just one particle weaving the fabric of reality by exploring every possible moment in history. Asterisk, now, we didn't quite make that theory work perfectly. There aren't enough positrons in the universe to match the electrons, but the idea captures the spirit of what I'm trying to tell you. The separation between past and future is a stubborn illusion. Asterisk, in the equations that govern the lights in this room, the atoms in your body, and the burning of the sun, the arrow of time does not exist. The machinery works both ways. Asterisk, we are used to thinking of the world as things happening, cause then effect. You push the swing, it moves. You strike the match, it burns. But that is just the macroscopic view. That is just the statistical average of billions of atoms crashing into each other. Asterisk, down deep, underneath it all, there is just a dance, a scattering, particles interacting, exchanging information, exploring pots. They don't know which way is tomorrow and which way is yesterday. They simply sum over the histories. They explore the possibilities. Asterisk, and out of that chaos, out of that infinite exploration of pots, rises the stable, solid world you see around you, the world where cups fall down and don't come back up. The stability of your reality is built on a foundation of absolute temporal chaos. Asterisk, so what does this mean for us? It means the universe is far more interconnected than we ever dared imagine. It means that history isn't a single line written in stone. It is a sum of infinite possibilities. Asterisk, we are just scratching the surface. We have found the rules of the game. We know how the pieces move. We know the bishop stays on its color. We know the electron can go backward. But we don't know why the game is played. We don't know who set up the board, and that's okay. In fact, that's the best part. Asterisk, people often ask me if knowing the physics takes away the mystery. If knowing the rainbow is just refracted light makes it less beautiful. I say, no, it adds to the beauty. It adds the beauty of the mechanism. It adds the mystery of why the mechanism is so elegant. Asterisk, you are sitting there in the middle of this vast, confusing, wonderful universe. You are made of particles that might be traveling backward in time right now. You are a bundle of quantum amplitudes summing up to a conscious being. Asterisk, that is a marvelous thing to be. Asterisk, we have so much more to find out. We have only just looked at the first few pages of the book. Asterisk, so if you want to keep reading this book with me, if you want to keep slicing the sausage and finding out what's inside, share this video with someone who thinks they know what time is. Shake their world up a little bit. Asterisk, nature is there waiting for us to figure her out, and she is far more imaginative than we are. Asterisk, I'll see you in the next one. Or maybe, if the electrons are right. I've already seen U.** and a video with the same gentle music, ending on a simple white screen with an electron taking the zigzag path.